The purpose of this video is to show where all the solutions come for this review for this Unit 1 Polynomials test. So we'll start with the multiple choice part of the review. The first question asks which one of the following is a polynomial function, and C is. This is a polynomial function because all the exponents are whole numbers only, 5, 3, 1, and of course you could call it x to the power of 0 I suppose in the end. This is a rational function in B, this is a trig function in E. This is not polynomial because of the root of x cubed. That would actually, if you simplified it, give you x to the power of a decimal or a fraction. For D, that's an exponential function because it's 3 to the power of x, or some function of x. For number 2, the range of a function is, and the y values isn't a very good definition. A better definition is the entire set of function values of the dependent variable. And by the way, for B here, the entire set of values for the independent variable, that's the domain. For number 3, what's the end behavior of this function? Well, the function starts in the third quadrant and goes through some hills and valleys or max and mins and finishes in the fourth quadrant. So from quadrant 3 to 4 would be the end behavior. For number 4, which of the following is true of polynomial functions? And C is the correct answer because x can only have whole number exponents. It can't have integer exponents unless they're positive integers only, because a negative integer would mean the exponent is no longer a positive number. For number 5, says consider the synthetic division, which polynomials were divided. Well, this 15 here is the constant term, and then that's the x term, the x squared term, the cubic term. So it would be 2x cubed minus 5x squared minus 8x plus 15 was divided by, and there's a 3 here, so it's divided by x minus 3. So that's why D is the correct answer. A is kind of close, but it says x plus 3. It's always x minus whatever this number is right here. Flipping over to number 6, the roots of this function, and it's in a factored form, so we can actually just set each of these to 0. So if we set x to 0, we get 0. If we set x plus 4 to 0, we get negative 4. And the 7/4 comes from setting that 4x minus 7 to 0. So if we do that, it would look like this: 4x minus 7 equals 0. If you take that 7 over to the other side, you get 4x equals 7, and then when you divide out the 4, there's the 7/4. So that's the other root. Now the factor theorem states, and A is the correct statement for the factor theorem, if p of x is divided by x minus c, and p of c is equal to 0, so that means the remainder is 0, then x minus c would be a factor of the polynomial. For c here, c says if p of x is divided by x minus c, then the remainder is p of c. That's actually the remainder theorem, but you're asked for the factor theorem here. In number 8, it says what set of numbers is illustrated at the right? Well, there's an open circle at negative 2, so that means you don't include negative 2, and it's shaded to the right of negative 2, which is means bigger than or greater than negative 2. So that's why B is the correct answer here. A is kind of close, but there's a less than or equal to sign, so if that dot was solid, then A would be the correct answer. For C and D, they both say less than or equal to, so C would be only if we were shading in the left direction here. For number 9, what is the correct division statement for this long division? And D is the correct answer because this polynomial was divided by 2x minus 3, and then we got a quotient of 3x squared plus x minus 4. Now, no remainder. So that means that this cubic should equal the product of 2x minus 3 and 3x squared plus x minus 4, which is what D says. Now, A is kind of similar to another correct way to write a division statement. Since this 2x minus 3 divided into this polynomial evenly, if you take that polynomial and divide it by 2x minus 3, and that's what this is saying right here, you should get 3x squared plus x minus 4. So if this 2x minus 3 wasn't there, then that would be another correct way to write the division statement. But it is, so D is the only correct answer here. For number 10, we're asked which of the following graphs illustrates a cubic graph with one real 0 plus another double 0. Well, if there's a double 0, then you're looking for this kind of thing where the graph just bounces off an axis, doesn't cross it, and then there's the other real 0. Now, if you're wondering where the word real comes from, real as a real number as opposed to an imaginary or complex number. If you remember when you're using the quadratic formula, if you use it and the number underneath the root, the b squared minus 4ac part, works out to be a negative, then that gives you complex or imaginary roots. And that's what's happening in A here. There's a real root in A, and then the function comes down and dips up, but it doesn't cross the x-axis again. So that's producing a pair of complex roots. Same in D here. We got one real root here, and then a pair of complex roots over here. In C, there's actually three real roots. One there, and of course another one over here. Three distinct real roots, that is. In part number 2, you're asked to show all work in the space provided, and it says there's 5 overall communication marks for part 2 for showing your work. Now, question 1 is the only one where you don't have any work to show. The rest, you're asked to show how you're getting your solutions. And that's because number 1 is a matching question. You're given equations and asked to match the graph with it. So notice that this is the highest power of x in the first one, so it's a positive, the leading coefficient is positive quartic. Quartics have loosely the shape of a W or an M, depending on whether they're positive or negative. And this one's positive, so that's why graph number 3 is the one that matches with this. Starts in quadrant number 2 and ends in quadrant 1. That's what a positive quartic does. In B, it's a negative quintic or fifth order polynomial, and a negative odd always starts in the second quadrant and finishes in the fourth. And this kind of, if you look at it, don't look at it too closely, you might think it's only a cubic, but there's a couple of additional going up, going down, max and mins here in the middle, which means it's not just a cubic, it's actually a quintic. For C, not number C, but question C here, it's a negative quartic. And so this is a negative quartic graph, starts in the third quadrant, ends in the fourth. And for D here, it's a negative cubic. So negative cubic starts in the second quadrant up here and ends down here in the fourth quadrant. For question number 2, it says determine the x-intercepts and then draw a possible graph. To get the x-intercepts, you set each of these factors to 0. So if we set negative 0.5x to 0 and solve for x, so we divide the negative 0.5, then you get x equals 0. So that's why there's a root right here. If you set the x minus 3 to 0, you get 3. Remember, you add 3 to both sides or move the 3 over. So there's a root over here, 3. And then the x plus 2 squared, we set that equal to 0. To get rid of the square, we take the square root of both sides and get x plus 2 equals 0, so x would be negative 2. So that's the third root. Now, the square, remember, means it's a double root, and this would be a negative, okay, quartic, actually, because there's a power of 2 here. 1 more makes 3 and 1 more makes 4, so it's a negative fourth order polynomial or quartic. So we'd have to start in the third quadrant up here, come and bounce off the x-axis at negative 2, have a minimum somewhere in between that and where it crosses at 0, and then go up, come back down, cross at 3. Now, this graph is actually drawn fairly accurately. If you only came, let's say, up to 9 or something like that, instead of it's a little over 13 here, that's not a big deal because you're just making a sketch of this graph. For question number 3, you ask, what's the remainder for this division? And I've shown 2 ways to get the remainder theorem and also using synthetic division. So the remainder theorem, what you do is you take this polynomial and you would substitute 2 in, x minus the number. So we put 2 in place of x. So 2 to the 4th is 16, times 2 is 32. 2 squared is 4, times 3 is 12, so minus 12 here, and 5 times 2 is 10, so you're subtracting 10 here, plus the 7, and all that adds to 17. Now, if you're doing the synthetic division, you don't have to worry about this remainder theorem, but for the synthetic division, notice there's no x cubed term. So you have to remember to put a 0 there. Because remember, this is 2x to the 4th, this is no x cubes, and then this is the negative 3x squared. So don't forget to put that missing coefficient in if there is a term that isn't existing in the polynomial. And so we put the 2 here, so we bring this 2 down. 2 times 2 is 4, and we add the 0 and 4 to get 4. 4 times 2 is 8, so 8 here, and add to the negative 3, you get 5. 5 times 2 is 10, so we put a 10 here. Added to the negative 5 is positive 5. And again, one more time, 5 times 2 is 10 here. 7 and 10 add to 17, so the remainder would be 17. For question number 4, it says solve completely by factoring. And so I've included a graph over here which shows, well, you can get from it what the roots probably are, so you can choose numbers for the synthetic division that probably work. And so it looks like there's a double root at negative 2, and then it also crosses to positive 2. So let's start with negative 2 here. 3, 5, negative 12, negative 20 are the coefficients. So we bring this 3 down. Negative 2 times 3 is negative 6, and add 5 to that to get negative 1. Negative 1 times negative 2 is positive 2. Add to the negative 12, get negative 10. And negative 10 times negative 2 is 20. So we add that to negative 20, you get a remainder of 0. Now, the negative 2 actually doesn't work a second time if you do the synthetic division. There actually isn't a double root there, and I'll talk about that a little bit right at the end here before we go on to the second one. But it looks like positive 2 will work, and it does actually. So bringing the 3 down, 2 times 3 is 6, add to the negative 1 is 5, 5 times 2 is 10, and of course add to the negative 10 is 0. So we get a remainder of 0 again. So the factors would be x plus 2 from that division, and then x minus 2 from that one, and then right at the bottom it says 3, 5, so 3x plus 5 is the other factor. If we set x plus 2 to 0, we get negative 2. We set x minus 2 to 0, we get positive 2, and then the 3x plus 5, bring the 5 over, it becomes negative, divided by the 3, you get negative 5/3. Now the negative 5/3 is about negative 1.6 repeating. Actually, it's exactly negative 1.6 repeating. So there actually isn't a double root there. It comes up across at negative 2 and does a little bit of a maximum, and then comes back down at negative 1.6 repeating. So there actually are two roots that are there that are really close together. So that's why there isn't a double root there. Moving along to the third one, we're trying to solve this equation, and I've included the graph for this one. This is a quintic, a fifth order polynomial, so this is it. There's actually, I'm not including the part that goes here, but so it looks like there's roots at negative 1, 0, something between 0 and 1, and also at 4. Now, notice that this has a common factor of x. There's no constant term in the end, so you can factor an x out. And so this is all we're actually factoring now. So the second graph is actually the graph of this one. So a different graph, but notice the zeros are all the same again, except this doesn't have a 0 of the number 0 like the x does. That would actually have a solution of 0 when you set x equal to 0. So otherwise the roots are the same. See, a root of negative 1, a root of negative 1. A root between 0 and 1, same here. And then a root of 4, same there. So this one has the additional root because it has the additional factor in it. So let's do the synthetic division. 3, negative 8, negative 17, 2, 8. So that's what goes across the top. And so it looks like there's a double root at negative 1. And actually, if you do negative 1 in the synthetic division, it does work twice. And I did 4 as well because it looks like 4 is a root 2. So 4 gives us this. So this would be x plus 1 squared. And don't forget about the x factor too. And then x minus 4. And then the bottom, that means 3x minus 2. Now, I didn't mention this in the first one, but it's a really common, it's not really a mistake, but you're stopping too early. It's a really common mistake in these kinds of questions to stop right here and forget that you're solving an equation and just factor it. It's an equation you're asked to solve. Notice the equals 0. If you're only asked to factor this, then it would actually stop right there. So it's an equation that you're trying to solve, and so we have to set each of these factors to 0. So we set x equal to 0 and get 0. If we set x plus 1 to 0, we get negative 1 for a solution. X minus 4 gives us 4, and then 3x minus 2. Bring the 2 over, becomes positive, and then divide out the 3, so you get 2/3. So those are the 4 solutions for this quintic equation. For number 5, it says show that x minus 1 and x plus 2 are the only, okay, there's the important word here, only factors of this polynomial. Now, and you've given a hint here, it says factor the polynomial completely. So, I write out the synthetic division, 1, 2, negative 3, negative 4, 4, so that's the numbers there. So it's telling me that x minus 1 is a factor, so let's divide it by 1, or x minus 1, so we put a 1 here. So do the synthetic division, you get a remainder of 0, and actually I did it a second time, 1 again, and actually got a remainder of 0 again. Now, I suppose I could have tried a third time, but actually it won't work. So let's move to the x plus 2. So negative 2 here in the 1, 4, 4, which is actually x squared plus 4x plus 4. And you get a remainder of 0 again. So the 2 1s here means that this factors into x minus 1 squared. And the negative 2 here means that x plus 2 is a factor, and another one here. So remember, the 1, 2 would actually mean another x plus 2. So x plus 2 squared times x minus 1 squared is what that factors into. And so factoring it like that shows that those are the only factors of this polynomial. For number 6, it says, what is the value of k if this polynomial, notice the k right here, when it's divided by x plus 2, the remainder is 27. Now, so that last part says if the remainder is 27 when the polynomial is divided by x plus 2, that would mean that the polynomial's value at negative 2 would be 27. So let's find what p of negative 2 is. So in this polynomial, let's put negative 2 in place of x. So p of negative 2, so negative 2 goes there, and of course multiplied by the k as well. So negative 2 cubed would be negative 8 times 2 would be negative 16. Negative 2 squared is 4 times 8 is 32, and of course this multiplies to 2k plus the 1 on the end. Now if you add all this together, those two add to 16 plus 1 would be 17. So p of negative 2 is 17 plus 2k. Now we're told that the remainder is supposed to be 27, so this should equal 27 if the remainder is 27. So we set that equal to 27 and solve for k, and we get 5. So that means that k has to be 5. So if k is 5, when this is divided by x plus 2, the remainder would be 27. Now, notice that this is going to would be marked as a thinking question, so it's very important to show your process or how you solve this. That's what I'm looking for when it says thinking. Thinking and inquiry. Last page here says solve without using technology. So we've got a couple of, or actually 3 inequalities to solve here. So 4x minus 12 is less than 7x plus 6. So this is just a linear inequality. So I'd bring the 7x over here. Notice the sign changed, and the 12 too. It becomes plus 12 on the right side. So that's negative 3x, and that would be 18. And then we divide out the negative 3. Now notice when we divide the negative 3, the inequality switches sign. That's my note here. Because whenever you're dividing or multiplying an inequality by a negative, it switches the direction of the inequality. If you're wondering why that's true, consider this. If you had the inequality 2 is less than 5, if we multiply both those numbers by negative 1, I would have negative 2 here and negative 5 here. Now 2 is less than 5, but if I put a less than sign here, that's not true. Negative 2 is actually greater than negative 5. So multiplying by negative switches the direction. So when we do the division here, we end up with x would be greater than negative 6. So that's the solution to this inequality. For b, we have a quadratic one. So we have to, well, the method I'm going to show you is one where you find the roots and then check the signs of this. We're looking for this where this is greater than 0. So if you factor x squared minus 2x minus 35, look for two numbers that add to negative 2 and multiply negative 35. That would be negative 7 and 5. So if you set each of these to 0, this graph would actually have zeros at 7 and negative 5. So it divides the number line into 3 intervals. Below negative 5, and then between negative 5 and 7, and then above 7. So it's kind of like this is negative 5, and this is positive 7. So below negative 5, between them, and above 7. And what we're going to do is check the sign of each of these factors, and then the whole thing to see where it's positive, where it's negative. So for x plus 5, if you think of a number below negative 5, like let's say negative 6 or negative 7, if you put those in place of x, negative 6 plus 5 is negative, so it's negative in that interval. The below negative 5, if you take a number below negative 5 and subtract 7, it's also negative. Like for example, negative 6 or negative 10 minus 7 is still negative. Now, this is the product of these two, so a negative times negative is positive. So it would be that's positive on that interval. Then we go between negative 5 and 7. So a number like 0, for example, is between negative 5 and 7. So we put 0 in here in place of x. This works out to be positive. 0 plus 5 is positive. 0 minus 7 would be negative. That factor is still negative. And the product of a positive and negative is a negative. And then above 7, like for example, let's say 8. 8 plus 5 is positive. 8 minus 7 is positive. And so the product of these two would be positive down here. Now we're looking for where this is greater than 0, so we're looking for this, and of course the intervals that go with them. This one here is positive on that interval, so one solution is where x is less than negative 5, and of course this one here is where x is greater than 7. So the solution is where x is less than negative 5 and also where x is greater than 7. That's the places where this quadratic would be greater than 0. Last one here is a cubic inequality. So we have to factor this 2x cubed minus 7x squared plus 2x plus 3. And so I've actually drawn a graph of it here. And so it looks like there's a root at, well, between 0 and -1, but whole numbers at 1 and also at 3. So that's why in the synthetic division I've used 3 here first. I could have started with 1, it wouldn't have mattered. So I did a division and I got a remainder 0, and then I also used 1, 2 and got a remainder 0. So just shows that the factors are x minus 3, x minus 1, and then 2x plus 1. So those are my 3 factors. So when I set x minus 3 to 0, I get 3. X minus 1, I get 1. And then the 2x plus 1 gives me negative a half. So if you have 3 roots, then there's 4 intervals. So first of all, if you put them in order, the negative a half, the first interval is below negative a half, and then between negative a half and the 1, and then between 1 and 3, and then above 3. So those are the 4 intervals we're going to check each of these factors on. So below negative a half, like negative 1 for example, negative 1 minus 3 is negative. Negative 1 minus 1 would also be negative, and negative 1 times 2 plus 1 would still be negative. So this is the product of 3 negatives. So remember, the product of an odd number of negatives is negative. And then we turn to the next interval. So between negative a half and 1, for example, 0. 0 minus 3 is negative, 0 minus 1 is negative, so they're both negative. 0 times 2 plus 1 would be positive, so that factor has turned to be positive. So the product of a negative and a positive is positive. So we have a place where the cubic is positive now. Next we check between 1 and 3. So for example 2. 2 minus 3 would be a negative, but 2 minus 1 would be a positive. 2 times 2 plus 1 would be positive. That would actually be 5. So we have the product of a negative, a positive, and a positive. So that would be negative because there's only one negative in that whole product. And then above 3, everything ends up being positive. That's going to be positive, so are all 3 of these. So everything's positive, so the product of all of them is positive. Now we're looking for where this is greater than or equal to 0. So we're looking for where it's positive, basically. So that positive comes from that interval, and that positive comes from that interval. So the solutions would be, now notice this is just less thans. This says actually less than or equal to. So we would actually include the endpoints. So I wouldn't just say this. I'd say where x is greater than or equal to negative a half and less than or equal to 1. And also where x is greater than or equal to 3. So those would be the solutions for that last cubic inequality.